To design a locality-aware algorithm, you need a machine model. We'll use a variation on the von Neumann architecture. Here's a picture of von Neumann from 1956. The von Neumann architecture has a processor. For the moment, assume the processor is sequential. This processor does basic computing operations. These are things like addition, subtraction, branches, and so on. Now the processor connects to a main memory. You regard this memory as being nearly infinite, but really slow. Hang on, I'm a-comin', I'm a-comin'. Between the processor and the slow memory, there's a fast memory. However, the memory is also small. Let's denote the size of this memory by capital Z measured in words. You're probably already familiar with two-level memory hierarchies. Consider, for example, a real processor like an Intel Ivy Bridge multi-core processor. The fast memory might be, say, a last-level cache that sits between the slower main memory, not shown in the photo, and the processor. Or what about this example? This is an Adaptiva Parallella board which is collecting dust in my office. It's collecting dust mostly because I'm sitting around drawing cartoons instead of doing, say, real hacking. Do I even know how to program anymore? The Parallella has a slow, non-volatile SD card which acts as a disk. It also has a smaller amount of main memory. Pulling data out of main memory is a lot faster than pulling it off the SD card. Okay, where was I? All right. There are two rules about how computations run in this model. Here's the first rule. The processor cannot do any operations unless the operands sit in fast memory. I'll refer to this as the local data rule. Here's the second rule. It's called the block transfer rule. It says that when data moves back and forth across this channel between slow memory and fast memory, it does so in chunks of size L words. That is, consider the following scenario. Suppose you want to load a word at address X from main memory. The block transfer rule says you actually have to pay to move an additional L-1 nearby words. Now, which words come with the word at X depend on how your data is aligned in slow memory. In other words, when you design an algorithm in this model, data alignment might be another issue you have to consider. Still, most real-life memory systems do block transfers. So you need to think about multi-level memories and block transfers when designing high-performance algorithms, like it or not. As I've stated it, this model implies two major costs you need to think about when designing algorithms. First, how many operations does the algorithm require? In other words, what's the computational work that the processor needs to do? Just like the concept of work in the work span model for a parallel machine, the concept of work in this I/O model will generally depend on the input size n. Then there's the second cost. How many block transfers does the algorithm need to do? As you might expect, the number of transfers might depend on both the size of the fast memory as well as the block transfer size. Let's denote the number of transfers by Q and refer to it as the algorithm's I/O complexity. To make this more concrete, let me walk you through a very simple example. Suppose you want to sum the elements of an array of size n. You know the processor needs to do at least n-1 additions, or asymptotically, that's big omega of n operations. What about memory transfers? Intuitively, you know you need to make at least one pass through the data. That suggests a natural lower bound on transfers. That's the ceiling of n divided by L. The ceiling accounts for the fact that if n is not a multiple of L, then you need to pay for a partial transfer somewhere. Now there's another thing to notice about this expression. It does not depend on capital Z, the size of the fast memory. That makes sense, right? You only need to touch each element once. So whether the fast memory is very large or very small, it really doesn't matter. Reduction does not reuse data. And not reusing data is bad.